In this video, I'm going to explain to you how to calculate the molar heat of solution of various salts. This is a typical problem that you might be asked to solve. Now we're going to assume that 1 milliliter of water weighs exactly 1 gram. First of all, a note about the specific heat capacity of water. On the data sheet that you'll be given when you sit for the HSC, the specific heat capacity of water is given as 4.18 times 10 to the power of 3 joules per kilogram per degrees Kelvin. In your textbook, it's given as 4.18 joules per gram per degrees Kelvin. The two values are actually identical. You do need to make sure, though, that you are consistent with your units. On the data sheet given to you in the HSC, the value has been given per kilogram of water. In the textbook, the value has been given per gram of water. So if you are going to use this value here, you need to make sure that you convert the mass of water to kilograms. If you are using this value, you need to keep the mass of water in grams. Okay, in this calculation, the first step involved is to calculate the amount of heat that is released or absorbed as the salt dissolves. To do this, we use the equation delta H is equal to minus mc delta T. Note that there is a minus sign in front of the m. Now in this equation, m stands for the mass of water plus salt. C is the specific heat of solution. Now we're actually going to assume that the solution is mainly water. So we take the specific heat to be the value that is given on the data sheet. Obviously the salt has a slightly different specific heat capacity to water, but the amount of salt is tiny in comparison to the water, so we can pretty much assume that the solution is mostly water. And delta T is the change in temperature. Now to make sure that you end up with the correct sign, you need to always make sure that you do the final temperature minus the initial temperature. So the equation is delta H is minus mc delta T. Mass in this case is 102.6 grams, that's the mass of the water, plus 2.023 grams, which is the mass of the salt. We need to convert this to kilograms, so I've divided it all by 1,000. So that gives me a mass of 0.105 kilograms. You'll note that I've rounded off this value. However, I have stored the value with all the decimal places in the memory of my calculator. Delta T is the final temperature minus the initial temperature. So delta H is minus 0.105 times the value from the data sheet, so 4180, times minus 1.42. My final answer is 621.0 joules. Notice that it's a positive value, and at the moment it's in joules. It's often more convenient to deal in kilojoules when we are talking about energy values, because the energy values tend to be quite large. So for this reason, I have converted this value to kilojoules. So it's actually 0.6210 kilojoules, remembering that there are 1,000 joules in 1 kilojoule. Step number 2 is to calculate the number of moles of salt. To do this, we use the equation N is mass over molar mass. Now the salt in this case is ammonium nitrate. That's the formula for ammonium nitrate. So the molar mass, I'm just looking up all the values for these various elements on the periodic table. If I add up all of those values, I end up with a molar mass of 80.04 grams. So the number of moles is the mass of salt, 2.023, divided by the molar mass, 80.043, which turns out to be 0.02527 moles. And the final step is to calculate the molar heat of solution. So that's the amount of heat that is absorbed or released per mole of salt. The equation that we use is that the heat of solution is delta H divided by N. Delta H we calculated earlier to be 0.6210 kilojoules. N we've just calculated to be 0.02527 mole. When I put that into my calculator, it turns out to be 24.57 kilojoules per mole.